Okay, welcome back. And this is our second session on our third day. Today, so I have to tell you guys this story. So when I was a new postdoc at the University of Toronto, I was so excited to be, Jim Arthur was there and Steve Kudla and Henry Kim, but I was a young mathematician, maybe not young in age, but a young mathematician. And I'm walking down the hallway and I, learned L functions from Henry Kim's book, one of his books. And so I felt like I knew him, even though I'd never met him. So when I see him down the hallway, I go, Henry Kim. And he just looked at me like I am insane. So as I'm getting ready to introduce him, I really want to say, Henry Kim. But he will be giving us a talk on the Fourier expansion of Gan-Gurevich lift on the exceptional group of type G2.
Thanks for the introduction. Anyway, I have been Jim's colleague for the last 24 years, and I've never seen him get sick. So he always come to office 3 times a week, and I hope I can be that healthy when I'm his age.
You are in your office every day.
Anyway, I wish him all the best for many years, more years of productive work. Okay, so the goal of my talk is to construct quaternionic modular form on G2, exceptional group of type G2, explicitly. So the emphasis on explicit construction. I'm not just satisfied with just giving a representation, but I want to get the Fourier expansion, very explicit Fourier expansion. So yeah, I will explain. So let me just start with the Ziegler modular form, so we will understand what I'm getting at. So the Ziegler modular form is a holomorphic function on the Ziegler upper half space. So Hn is x, y, xy symmetric n by n symmetric matrices over R, and Y is positive definite matrix. And so rho is the irreducible, so let's say irreducible representation of weight K1, Kn, K1. So then the Ziegler modular form is defined as a holomorphic function. So this is called Ziegler modular form of weight K bar. So let's do K bar. If F rho CG plus D FC. So gamma is in symplectic matrix, and F is holomorphic. And n equals 1, of course, you need the condition on the cusp, but I will just omit that. So if rho is special, it's a determinant of K. So in other words, this is K. So in the case, then you get scalar valued Ziegler modular form. So then F is called classical Ziegler modular form. Of weight weight k. And it has a Fourier expansion. So Fourier expansion, the f. So in this case, 2 pi I trace of t z. So t is half integral positive semi-definite. So if it is a cos form, it will be just the positive definite, sum of positive definite matrices. And this is called Fourier coefficients. This has many arithmetic properties, many arithmetic information. So for example, so one example is like a theta series. For example, you have a Q, let's say QA is M by M matrix. And let's say QX is integral positive definite quadratic form. So then you can form this theta series. So trace of QX or Z, where X is in M by N matrices over Z. So then this becomes a Ziegler modular form of weight. M over 2. And so the Fourier coefficients are exact representation number of t by this quadratic form. So I'll skip that details. So now for this symplectic group, so UN is maximal compact. This is a maximal compact subgroup. And the quotient, so this quotient is isomorphic to this HN, the Ziegler upper half space. And this Ziegler upper half space is a complex structure. So this is complex structure. So this complex structure is responsible for the existence of holomorphic function. So you get the holomorphic function on this space. So especially if you look at the Adelaide language, so when you have a Ziegler module of, let's say, you can have Hecke eigen cos form. So then you can attach automorphic form on the Adelaide ring. So you have so you can consider Adelaide GSP2NA, GSP2NQ to C. And in this case, our Fourier expansion will take this value in this form. So let me write this 1x01. So let me write for future reference, I denote by nx times m. So this is e to the 2 pi I trace of tx e to the minus 2 pi trace of ty. So you have this kind of Fourier expansion, and then this phi f will give rise to representation on SP2n, so that you can have a infinite part, finite part, and then this infinite part, this becomes holomorphic discrete series. Discrete series of a Harishchandra parameter. So Harishchandra parameter is k minus 1 E1 plus k minus n En. So k is greater than n. Okay, so these are the Ziegler case. So now we want to do similar thing for exceptional group of type G2. So G2. So the thinking diagram is, so I'll use this notation. So alpha is a short simple root and beta is long simple root. And in this case, the maximal compact subgroup is SU2 times SU2. Divided by plus minus 1. So this is a maximal compact subgroup. Maximal compact. So in this case, unlike a Ziegler case, so in this case, the quotient has a complex structure. But in this case, the quotient, it has no complex structure. And so you cannot define a holomorphic function. But G2, so no holomorphic forms. But G2 has quaternionic discrete series. So let me explain quaternionic discrete series. So let's denote dk to be the quaternionic discrete series of weight k. So dk I'll denote by dk. So this is the minimal k type is vk is the symmetric 2k power on the first SU2 part, and then second SU2 part is trivial. So that's the minimal k type. And the infinitesimal character is k minus 2 beta 0 plus rho. So here beta 0 is the highest root, and then rho is the half sum of positive roots. So that's the quaternionic discrete series. So for us, important thing is that dk is a submodule of the degenerate principal series. So submodule of this is a sine k determinant of minus k minus 1. So here, P is the Heisenberg parabolic. So Heisenberg parabolic is associated with the short simple root. So here, Heisenberg parabolic is Levy decomposition is Mn. M is isomorphic to GL2. Do you have a question?
Is always, I mean, the action of plus or minus one. Minus one sometimes. 2K. Oh, it's 2K.
2Ki, so I that's why I. Okay. All right, so this is a quaternionic discrete series. So so then the story goes back to the Gan and Gross and Sabin, so that they define. So let me. So Gan and Gross and Sabin, so in 2002 paper, so define the quaternionic modular forms. On G2. So I'm not going to write down all the conditions. I will just simply say that F is a quaternionic modular form of weight K on G2 is so let me denote by this tau K. So this is a minimal K type, and so let's say tau K is map from K infinity to GL VK.
I was just wondering, is there only one form of G2 or is it split?
Split. Oh yeah, sorry. Yeah, I should have said split. There is a two form, split one and anisotropic one. So I'm dealing with the split G2. So okay, sorry. Thank you. So I'm dealing with the split form. So this is a VK check valued function on G2A such that, so there are various conditions. I'm not going to write all the conditions, simply saying that you have so it has a right invariant property, and there are some properties of I'm going to skip. So then F generates dk as an admissible representation of G2 R. Okay, so that's the quaternionic. So then the natural question is construct the quaternionic modular form. First of all, first we can get Fourier expansion of the quaternionic modular form. So Fourier expansion. So in order to get the Fourier expansion, we have to examine the Heisenberg parabolic subgroup. So P is Levy decomposition is Heisenberg, and this unipotent radical has a subgroup which is a commutator subgroup, and then this is also center. This is also the center of N, and the quotient. This quotient will denote by W. This quotient is isomorphic to binary cubic form. binary cubic. So the explicitly you get A1, A2, A3, A4. You can attach the binary cubic form. A1. Okay. So then let's say you fix additive character. So then the Fourier expansion along Zn is, so you have F0 plus Ft, where T is in non-zero rational numbers, and then Ftg is just simply all right. So this is just the Fourier expansion along Zn. So we can show that this kind of constant term contains all the information. So f is 0 if and only if f0 is 0. So you just have to study this f0 term, and f0 term has the following Fourier expansion. So SU2 is I think this is isomorphic to the quaternion group, the discriminant one. I think that's why it's called. I mean, the expert might explain for better. It's called. I mean, quaternionic. Normal, yeah. So this is isomorphic to the quaternion group of normal one, right? That's why it's called quaternionic. Okay, so we have a Fourier expansion of F0. So F0. So this you just have to look at this F0. So F0 has, so notice that so we are using this fact. The n minus Gn is isomorphic to the binary cubic form. So it has this Fourier expansion. So here FWG is so here psi Wn is psi Wx. So here here n is nx t in Na. So x is in W and t is in the rational number. So then the Pollock, so Aaron Pollock, 2020, he gave a very explicit Fourier expansion. So he can write down the Fourier expansion explicitly as follows: F00M plus so here so sum over positive. So this means that this binary cubic form has only the totally real. So FWX1 has 3 real roots. So it is sum over only on this element. And so this is a Whittaker function. So let me write down the Whittaker function. So Wm is sum over x k plus v y k minus v. So here xk plus v y k minus v is a basis for vk. So these are 2k plus 1 dimensional vector space. So and so let me write here and then I can hide. So this function is kind of this plays a role of exponential function in the Ziegler case. So this is given by some combination of Bessel K function and very complicated formula. So let me write down. PWJ JMI KV is the Bessel K function. So here PWZ is just the FW Z1 and the Z is MI is in the upper half plane and JMI is CI plus D to the third power determinant. So let's say M is ABCD in GL2. Okay, so this very complicated formula. So this plays a role of exponential function in the Ziegler case. All right, so in the same paper, so the question is, can we construct the quaternionic modular form? So in the same paper, Gan and Gross 7, they considered Eisenstein series. So Gan, Gross, and 7 constructed Eisenstein series. From degenerate principal series. So you have a degenerate principal series. So when you have this phi, then you can consider Eisenstein series. And they show that this is a modular quaternionic modular form weight 2k, and the Fourier coefficients. They also computed the Fourier coefficients, and Fourier coefficients are the zeta function attached to the zeta function. Let me write down AW2k discriminant of AW2k minus 1/2. So here AW is the cubic ring associated with the W is in the binary cubic form. So you have very interesting Fourier coefficients. So then in the same paper, they asked, can we construct a cos form? So that's the question. So then the question is, can we construct a cos form? And so it grows in a letter to David Pollack. So this is gross conjecture. So this is 2000. 2000. He conjectured gross conjecture. He conjectured the lift from the existence of weight K form, which is a lift from weight 2K, weight 2K elliptic modular cos form. So going from 2K to K. And so for example, Ramanujan delta function will weight 12 will go to weight 6 form. And also he gave very precise relationship. And also he conjectured the following. So let's say weight K form, let's denote by F0, and F0 NX M is, you have this A, so let me denote by AF. So let's say AF cos form F. So then you have, let's say we have this Fourier expansion. Then, and also since it's a cos form, you only sum over where the quartic, so this Q is the horizontal quartic form. So for the quartic form is negative, so you sum over only, this is because of the hospitality condition. So in that case, the gross conjecture, the relationship of, he gave precise relationship of this Fourier coefficient. So he conjectured that this belongs to the Hecke field, and it satisfies the following relationship, very similar to Walsh-Purgé formula. So you have rho tensor with F rho AW. So this is a Rankin-Selberg L function, and so rho AW is the two-dimensional representation coming from. So when you have a zeta function of this cubic ring, so it decomposes as zeta s and two-dimensional L functions. So that's the rho AW. So this is a Rankin-Selberg L function. So this is very similar to Walsh-Purgé formula between cos form and its half integral weight by Shimura correspondence. Anyways, this is he conjectured. So we try to prove that conjecture. So the first result is a Pollock, 2021. So he constructed the weight greater than or equal to 6 cusp form using theta lift. So theta lift between SP4 and SO44. So when you start with a form on SP4, so it's a Ziegler cusp form. So weight W. So then you get the by theta correspondence, you get so there is theta lift. And then G2 is a subgroup of SO44. So then you can restrict. So you can restrict to G2. So then he showed that this is a cusp form. The cusp form on G2 of weight W. Weight W. But because of this restriction property, so he could not show that this is a Hecke eigenform. But if weight 6, if it's weight 6 and Dalal showed that dimension, he showed the dimension formula. So Dalal showed that the dimension of weight 6, level 1, this is 1. So in weight 6 case, you do get Hecke eigenform. Okay. All right, so then all right, so now let's start with a weight 2K form, weight 2K cusp form on let's do level 1 case. Let's just do level 1 case, SL2Z. So then you have a representation. And so pi infinity is a holomorphic discrete series, and pi p is a principal series, mu p inverse. And so then from this, you can consider degenerate principal series. So let's denote by capital P pi. So this is the degenerate principal series. So the determinant, you get 0 there, 0. So we can show that this degenerate principal series is irreducible. This is irreducible. So this is defined for all p, and so then we let pi infinity to be so you can form so pi infinity. So we put the pi p this one, and pi infinity is a quaternionic discrete series. So then you can form formally this this is a irreducible, admissible representation of G2A. So we have this formal representation. So the question is this automorphic? So that's the question. So the question is, so is pi infinity automorphic? So in fact, we can actually construct some kind of function in this space. So we can construct FF in this space using degenerate Mittaka functions. And from the data from H. So H is a half integral waveform. So on the Shimura correspondence. So this is the weight K plus 1/2. So there is a half integral waveform corresponding to F. So you can, using this data, you can construct very explicit functions. It's a very formula is very complicated. I'll omit the formula. So we spend long time to prove that this is actually automorphic, and but we could not do it. So we could not show that this is automorphic. So we got stuck. So then what do? Then we try to circumvent the ways. So then we examine this degenerate principal series. So and we realize that this pi p is actually the Langlands quotient of this induced representation Q. This Q is another maximal parabolic. So this is a maximal parabolic associated with beta, the long simple root. And so then this is a pi p tensor with determinant 1/2. So here Q has a Levy decomposition Lu, where L is isomorphic to GL2. So this is what we realized. So then you can see that this pi f, so pi f is nearly equivalent to this global induced representation. So if this is automorphic, so then it is a cap representation. So if pi f is automorphic, it is a cap representation.
Cuspidal, do you know that it's going to be cuspidal?
Which,
Cap. Why is it cap? It will be cuspidal if it's automorphic.
I think the fact that we put the quaternionic discrete series will imply that it's a cuspidal.
It will imply that.
Yeah, I think so.
Okay, just a question.
Okay. Okay, so this is a cap representation. So then so we realized that Gan and Gurevich in 2009, they indeed constructed a cap representation. So they constructed this cap representation using theta lift. So let me just briefly go through the diagram. So this theta lift be inside G2 and PG SP6, dual pair inside E7. So then you start with a pi f, where you need a condition that the central value is non-vanishing. You start with that. Then you consider sigma f, the cap representation associated to this induced representation of GL2, SL2, and SP6 pi f tensor determinant pi f. So you have and then you get the theta correspondence. So let me denote by theta E7 PG SP6 sigma f. And this is indeed the cap representation of G2. So then what we did was, so then this is a natural candidate. This is exactly what we want. So then, so Gan and Gurevich did not show the infinite part. So we show that this indeed generates quaternionic discrete series. So we showed so the theorem is that this generates a quaternionic discrete series. So we show that this is in level 1 case. So in higher level case, we cannot show it yet. So we need the author multiplicity formula. So I will explain after I write down the consequence of this theorem. So first consequence is that so we can show we can actually compute degree 7 standard L function. So you have a the degree 7 G2 has a degree 7 L function. So then so let me denote this by pi x. So the degree 7 L function this is given by symmetric square LS plus minus 1/2 pi f. Okay, so we have a very nice degree 7 L function. And then also orthoparameter. So we get orthoparameter of pi f. We can actually is a conjectural orthoparameter because the Langlands, we have to use the conjectural Langlands group. So let's say you have a conjectural Langlands parameter for f. And then so we have so you have this map from SL2, you go to beta C, SL2 attached to this long root times SL2 will go to SL2 3 alpha plus 2 beta C attached to the highest root. And then this is embedded into G2C. And then this composition will be our orthoparameter for our our cost form. Okay, and also we can show this gross conjecture, the part of this conjecture, when we cannot show this yet, but we can show this. We can show. So we can show this when the EW, this field is either Q cube or Q plus real quadratic. So of course, the most difficult case is when EW is the cubic field. But anyway, we can show this partially. All right. Okay, so the remaining 5 minutes or so, let me try to explain how we can extend this to general higher level. So wave 2K form correspond on let's say gamma 0 C, where C is square free. So then you get so you have this is holomorphic discrete series. Of lowest weight 2K, and the epsilon factor. So we have a formula for the epsilon factor. Symmetric Q of the epsilon factor is -1. And if a P does not divide C, so then pi P is pi mu P inverse. So in this case, the epsilon factor is 1. So in this case, the pi, so in the author packet, we denote pi plus to be the I erased. Oh, okay. You have the Langlands quotient. So let me denote by J beta 1/2 pi p. So this Langlands quotient of the induced representation from the other parabolic pi p determinant 1/2. And then if P divides C, there are two cases. Pi P is either Steinberg, twist by non-trivial quadratic character. So this is non-trivial quadratic character. So in this case, in ortho packet, pi p plus is the Langlands quotient, and pi p minus is the Langlands quotient of 1 pi 1 VP. So this is because we have the reducibility of the degenerate principal series mu p. So this is the degenerate principal series p to G2 mu p determinant of 1/2. So this is reducible, and the quotient is 1 MPP, and then we have sub representation 1/2 Steinberg VP. So this is the reducibility of this degenerate principal series. Now, this is p-adic. Yeah. But if pi p is Steinberg, then it becomes very complicated. And this degenerate principal series is reducible, but it's much more complicated. So then this is we have again the same and V and 0, but this sub representation is not irreducible. So we have another pi 1 J beta 1/2 Steinberg 0. So you have so this V is not irreducible. So you'll have a decompose like this again. And so in this case, so we don't know what to put. So in this case, pi p will be natural. So it's just the naturally 1/2 pi p, but so pi p minus, we don't know where to put. I don't know what to put. So we'll just assume that. So we assume that the S0 is empty. So S0 is set of P, where pi p is Steinberg. So we assume that this is empty set. We simply assume that. So then the conjecture, so ortho multiplicity formula, conjecture. So I'm done writing after this. So you look at this representation, pi p minus p is in S prime. So S prime is a subset of P divides C. And then pi p plus P is in S So we consider this representation, and this occurs with a multiplicity 0, 1 in L2 space, so it is in L2 space. And it's multiplicity 1 if and only if the epsilon factor symmetry cube, the global epsilon factor is -1 to the number of S prime plus 1. So i.e., this number is even. Okay. So that's the multiplicity formula conjecture. So if you assume this conjecture, then we can prove that the form we constructed, is automorphic. Okay, so that's all I want to say. Okay, thank you.
Thank you.